есть, куда их сейчас что-нибудь придумаю в перерыве?
Да, ну, я, наверное, если вам флешка не нужна, то
Нужна. Сейчас что-нибудь придумаю.
ну, можно, наверное, там сходить куда-нибудь.
Да, я думаю, что...
Кто-нибудь из местных компьютеров.
Угу. Трансляция идет, меня слышно, да? Угу, хорошо. Well, let's start our lecture. I just want to recall, in the beginning, I want to recall one point. I said it during the last lecture, but very quickly in the very end, so I prefer to do it once more. Once more, if we have such a short exact sequence of groups, then now I just would like to recall that the associated Hochschild-Serre cohomological spectral sequence is obtained starting from the bicomplex. We need to take, I recall that F is a resolution of Z over group ring of G, and P, projective resolution, of course. P is a projective resolution of Z over ZQ. And then this is nothing but such home over Q of well, and M is an SG module. So I just recall that we take such double complex with differentials increasing the gradients. The first differential is induced by differentials by the differential in P, and the second is induced by one moment. Sorry. One moment, some problems here. I have Q here. The first differential is induced by differential here, and the second is induced by the differential in F. And I just would like to recall that this double complex, in a standard way, which we discussed during the last lecture, produces the spectral sequence. This is the zeroth term of this spectral sequence. Now the zeroth differential is D2 primes, so it is induced by this. And then the first page is, as we have discussed, and finally, the second page is the cohomology of Q with coefficients in this group. Okay, all this stuff was on the last lecture. The only thing I would like to discuss in more detail is the multiplication. Here we have multiplication. We have discussed that once we have multiplication in double complex, such that this multiplication satisfies the Leibniz rule with respect to both differentials d2' and d', then we automatically have multiplication in all terms of the spectral sequence. We discussed this, but now why do we have multiplication here? Because this is the same reason why we have multiplication in usual cohomology. Because we have for each projective resolution of some of Z over some group ring, we always have approximation of diagonal. We always have such maps and these maps turn this is co-multiplication on the level of resolution, and it turns to multiplication on home. So we obtain multiplication on cochains and automatically on chains. The only thing which I would like to stress that this is completely the same way as we obtained multiplication in cohomology. So it is not surprising once we introduce multiplication here by means of such approximations of diagonals, it is not surprising that on the level of E2 we get directly the same multiplication as in cohomology. What does it mean in this situation? Actually, when we have multiplication in cohomology, there are two ways to look on this. First of all, if we have cohomology of some group with a ring on which the group acts trivially, then we have a multiplication then this object becomes a ring. So we have multiplication inside this cohomology. But if we have coefficients in any G module and we have coefficients in any other G module, then we also have multiplication defined in the same way, but the result goes to cohomology of G with coefficients in tensor product of these modules. Tensor product just as abelian groups, and the structure of G module is obtained by diagonal action. So this is the most general situation, and when we discussed multiplication, we actually constructed it in this way. Just if M and N are both the ring R, then we can further map from R cross R to R. This is just multiplication in the ring R, and we get these are usual multiplications. So these are two ways to look on the same object. So we have generally we have multiplication of this kind, and then how to introduce multiplication in this object. There is natural way to turn this into yes. What I assume, as in the previous, let us assume, as on the previous lecture, I prefer to consider the following partial case. Assume that M is some ring with trivial action of Q, of H. Actually, with trivial action of G. Let it be with trivial action of G. Then, look, if we have I would like to construct multiplication. As multiplication should go from here to here. How does it look like? We start from pth cohomology of Q with coefficients in qth homology of H with coefficients in M. In R, I take now S cohomology of Q with and tth cohomology of H with coefficients in R. Okay, I just wrote down this left-hand side. Now, what can we do? First of all, we can apply this multiplication mu in this situation. Look, we have cohomology of the same group with coefficients in two different modules. Okay, then we can get into the P plus S. This standard multiplication leads us to P plus S cohomology of Q with coefficients in the following group. But now we may consider multiplication for cohomology of H. And we have a natural map multiplication this leads to K plus T, the homology of H with coefficients in R. Since R is a ring with trivial action, then we have this multiplication. And now, well, let this again. Let this be mu Q, since it corresponds to the group Q, and this one will be mu H. And here, now we apply the, well, when we have a homomorphism of coefficients module, then we definitely have the induced homomorphism of homology groups with this module. And so we apply this induced homomorphism, and we get into P plus S group of Q with coefficients in Q plus T cohomology of H. And this is exactly E2 with number P plus S, Q plus T. So I just have described how the multiplication in E2 looks like. The matter is why the multiplication looks like in this particular way. Because the multiplication is induced by the multiplication here. And these two multiplications, this one and that one, are induced by co-multiplications here and here respectively. So more or less this is a tautology. Just to understand that it is tautological, you need to write down explicitly what we discussed last time in all details. But in fact, it is tautology that this multiplication is induced by diagonal here. This multiplication is induced by diagonal here. And this multiplication here is induced by both diagonals at all. So in fact, we have two multiplications. We have multiplication here, and then we can induce multiplication in E2. Or we can just consider this. And this is the same, since they're both induced by the same approximation of diagonals. To be precise, they are the same up to a sign. Actually, here is hidden a sign. Here we swap this S cohomology and Q cohomology. To be honest, we need to add here -1 to the power QS. And in those sign convention, which I use that differentials anti-commute and so on, there are other sign conventions, and here you get other signs. These signs are not important. These signs are just so well. This is just useful observation that multiplication in E2 of the Hochschild-Serre spectral sequence is of this particular form, is of this particular easy. It is very natural associated with multiplication and cohomologies of H and Q. Well, and now I want to discuss one more example. Actually, we have started from rather complicated examples. We have already discussed pure braid groups and so on. These are not easy examples. But now I would like to start to return back to one very easy example, which we have already discussed, actually. And we have discussed it maybe on the first or on the second lecture. And actually, but we have discussed this cohomology without multiplicative structure. And now I would like to return back and to obtain the same results from, well, I forget to say what I'm talking about. I would like to consider the cohomology of cyclic group again. And now I would like to consider the cohomology of finite cyclic group, or say of prime order P. And now I would like to consider it from the following point of view. Let us take such sequence Z, Z, and ZP. And apply all this stuff with the spectral sequence. Okay, so I would like to consider one particular short exact sequence of groups. Here we have just multiplication by P. Let P for simplicity be prime. And I would like to apply the Hochschild-Serre spectral sequence to understand the cohomology of ZP. We have already computed this cohomology in different way, just by constructing easy explicit resolution for Z over this group. But now let us do the same computation in by another method. First of all, let us recall that, of course, we know the cohomology of Z. Yes, the group Z, for the group Z, its classifying space is just circle, and of course we know all its cohomology. 0-dimensional and 1-dimensional is Z, and all other are trivial. But okay, for simplicity, let us start with considering we can take different rings of coefficients. First, let us take for ring of coefficients the same ZP, but with trivial action of our group. Okay, now let us try to consider the spectral sequence. Okay, what can we say? We have, if we, but the only thing I prefer, the usual notation is E2PQ, but P is now not a good index, so I will write S and T. But this is the only difference. Okay, what is E2ST? By our general construction, it is S cohomology of, look, the most standard way to apply an Hochschild-Serre spectral sequence is that we understand cohomology of subgroup and of the quotient group, and we try to understand the cohomology of the middle group. But this is not the only possibility. Now we have completely different situation. We very good understood cohomology of these two groups, and we try to understand the cohomology of this group ZP. Okay, so what we have here, the term E2 is given by, so this is H and this is Q, so here is ZP with coefficients in Tth cohomology of Z of H with coefficients in R, in ZP. Okay. Now, first of all, let us understand what is written here. Of course, this is non-trivial only if T is either 0 or 1. Otherwise, this coefficient group is 0 and everything vanishes. So our spectral sequence is contained only in two rows, T equals 0 and T equals 1. Next, okay, we know that H1 of Z with coefficients in ZP is, of course, ZP. Yes? Since it's the cohomology of the okay, the zeroth cohomology of any group is the ring itself. Okay, and of course, look, generally here we have cohomology with twisted coefficients. Generally, the group H can act, the group Q, this one is H in our old notation, and this one is Q. The group Q can act on the cohomology of H. But of course, on zeroth cohomology, the action is always trivial, since it's just the coefficient ring. It is canonically isomorphic to the coefficient ring, and here the action is trivial. I would like to say that well, now look, H1 of Z with coefficient ZP is again ZP. Again, this is the circle. But now the question, and actually here we have very easy interpretation. It is home from this group to ZP. H1 with untwisted coefficients is just home from our group to this coefficients group. And of course, this is ZP. Yes, and this Z is this is H. So this is H, and this is H. This is this Z. Yes. And now look, this Z is central in G, and hence the action of Q on H is trivial, and the action of Q on this home is also trivial. When we conjugate an element of H by an element of Q, then of course we get the same element of H. Here we have very special case when H is central in Q, in G. The action of ZP on this group for t equals 1 is again trivial. So in fact we have untwisted coefficients in all cases. Well, so what does it mean? This means the following: that our spectral sequence has the following form. We have two rows, t equals 0 and t equals 1, and in each row we have cohomology of Zp with coefficients in Zp, with untwisted coefficients. And this is what we want to this cohomology ring is exactly what we this is the term E2. The term E2 is as follows, and all we have zeros in all other positions. Look, in particular, what we have for S equals 0. Zeroth cohomology of Zp. This is the only thing we know, we definitely know. Not the only, but this is the thing that we definitely know. The cohomology of any group with coefficients in Zp is Zp. Well, but now I would like to understand the multiplicative structure here. Well, and the multiplicative structure here says that okay, a generator here is just the unit of this ring. We have here unit, which is unit of this ring, lives in the gradient 0, s equals to 0, and it is just before I draw this picture, here it was written how the multiplication looks like. The multiplication looks like the multiplication E2 st times E2 some s prime t prime looks like as follows. First, this is s dimensional. In this particular case, first of all, t must be 0 or 1. T prime must be also 0 or 1, otherwise it is trivial. And then this multiplication reduces to usual multiplication in cohomology here. So we first need to this is cohomology of Zp with coefficients coefficients are in both cases ZP, but I think of them as, well, okay. This is the usual multiplication of cohomology with coefficients ZP, but then I interpret these coefficients, this ZP may be either zeroth or first cohomology of this ZP. ZP is this group with T either equal 0 or T equal 1. And then after we apply this cohomology, we need to apply cohomology in that cohomology groups. Apply multiplication in that cohomology groups. And multiplication, so this is the multiplication in the first column. So let us denote here let us choose a generator iota of this group. And then, well, how the multiplication in the first column looks like. Okay, of course, 1 is 1, so 1 times iota is iota, and iota times 1 is iota. But iota times iota is, of course, 0, since we get into this. So this is just multiplication in this cohomology ring. This is here I have wrote multiplication in cohomology of Z with coefficients in ZP. It is very easy. We have generator 1 in 0th cohomology, generator iota in the first cohomology, and the product iota times iota is 0, since we have no, the second cohomology is trivial. And now,
Sorry, can you describe it in notation of H, G, and Q, or there is no?
Well, this Z is H, okay? But generally, the multiplication and cohomology of H can be complicated. But in our particular case, H is Z, and of course, its multiplication and its cohomology is very easy. It's just, so generally, we will get here, we will have cohomology of H. And it may be rather complicated. But in this particular case, the cohomology of H is very easy. And we have only generator 1 here, and generator iota here, and iota squared is 0. Well, but now, when we say that this row is cohomology of ZP with coefficients in ZP, again, this ZP is Q, and this ZP is this group. So this ZP downstairs is generated by 1, and then the ZP here is generated by iota. So when I try to multiply two elements in somewhere in this row, then I have S cohomology and S prime cohomology. And here, this ZP is generated either by 1 or by iota, depending on whether T is 0 or 1. So this is in the case T equals 0, and this is in the case T equal 1. These are, in both cases, this is ZP, but but it is generated by different. This is ZP generated by different. And similarly here, this ZP, which stands in coefficients, is generated by 1 or by iota, depending on whether T prime is 0 or T prime is 1. Well, now look, what happens when we multiply these two classes? First of all, if both T and T prime is 1, then the multiplication goes to the second row and we just get 0. But if we have any other situation, so not both T and T prime are 1, we have two situations. If both of them are 0, then we just get usual multiplication in this row, usual multiplication in cohomology with coefficients in here. But if one of them is 0 and another is 1, then these coefficient groups, one of them is generated by 1 and another is generated by iota. When we multiply, we get iota. So the multiplication goes as follows. We multiply an element here by an element here. We multiply them as usual elements in H star, and then we just multiply it, we interpret this ZP as generated by iota. So we interpret this as an element of the upper row. Algebraically, this means that E2 ST is just the tensor product of I prefer to write it without indices. E2, the whole term E2, is just the tensor product of the cohomology of ZP with coefficients in ZP tensored by exterior algebra over ZP with generated iota. Here, we take the tensor product of this row with this column, and this is exactly what we get. And I was explaining it for so long to stress that it is not only additive isomorphism. It is obvious that it is additive isomorphism, but this is isomorphism of rings. This is the crucial point. This is isomorphism of bigraded rings. So the first gradient lives here. The gradient in this ring is the first gradient, and the gradient here, where iota have gradient 1, and this is the second gradient. Okay. Now let us start studying differentials of this spectral sequence. Well, okay. Let us go slightly further. First of all, we can also say what is here. The matter is that the first cohomology is something that we know very well. The first cohomology of group with untwisted coefficients. So if G acts trivially on A, then we have discussed that it is just homomorphism from G to A. Well, and in our particular case, we have the first cohomology of ZP with coefficients in ZP is just hom from ZP to ZP, and of course this is isomorphic to ZP. So I recall that here we have this isomorphism. So here in each row we have cohomology, this cohomology, and so these two groups are again ZP. Well, and okay, I just want to choose a generator here, and once I choose, I just denote it by U. This is just notation, just I have this group, I choose a generator here. But then I know a generator here. A generator here, according to this isomorphism, is the product iota times U. So U is just notation, but I do not need to introduce new notation for this generator. This is just product of those two. Okay, but now at this moment we can start studying differentials. First of all, there can be only one differential. Only differential D2. This is by dimensional reasons. The matter is that differential D2 has, in cohomological spectral sequence, it has by degrees, by degree of D2 is 2 minus 1. So it goes like that, and so on in parallel. But all other differentials are trivial by dimensional reasons. They cannot be inside two rows. So we immediately see that, okay, we will study differentials D2 in a minute, but then we know that E3, after we study this differential, we obtain some term E3, and this is the same as E infinity. We have no further, all further differentials are trivial, so the groups do not change till the end. So this is the same as E infinity. But now we know the result. Our spectral sequence converges to the cohomology of the middle group. So the result is what, and we know very well what is the cohomology of Z with coefficients in Zp. It is Zp if n equals 0 or 1, and it is 0 otherwise. What does it mean? This means that when we study E3, which is the same as E infinity, then, well, here it is E2, but if we consider E infinity, which is E3, then on each diagonal we must have certain groups, this diagonal is some subsequent quotients for certain filtration in cohomology of Z. Well, so we must have here we must have some groups which are these subsequent quotients. But look, this cohomology is trivial if n is greater than 1. So, well, in a trivial group we have no filtration at all, so the only possibility is that all these groups must be 0. Well, just because we know the result, we know that we must have cohomology of Z here. But what concerning, okay, here we have Zp, and it is not surprising. The matter is that this Zp cannot be affected by differentials in any way. There is no differential from this cell and no differentials to it. But the same is here. Look, this Zp cannot change. We have differential from here is trivial, differential to here is also trivial. So we definitely have in Zp and Zp here, but the consequence is that we must have 0 here. The matter is that here and here are quotients of certain filtration in group Zp. If one of the quotients is Zp, then the other is trivial. So just by counting the elements.
And we must have at least Zp in total. Yes?
We must have exactly this Zp in total. We must have in total, we must have two groups, one of which is the quotient of Zp by the other two. But by the other one.
We have at least Zp in the
But we know that here we have exactly the Zp. Hence here we, yes, this Zp doesn't change.
Okay.
Hence here we have exactly 0.
Yes.
Well, what does it mean? This means that this, look, I don't know what is, we have such sequence of of differentials. And after taking cohomology with respect to these differentials, we get 0 in all these positions. But what is cohomology? Cohomology is kernel quotient by the image. Look, in each of these cells, for instance, in this cell, the kernel of the differential is the whole group. We do not know this group yet, but we know that it is the whole group here. But so once we must have 0 in E3, this says us that all these differentials must be surjective. This is the only way how to get 0 in E3. We must kill the whole group here. But similarly, now look on the first row, say this group. The image of differential is trivial. So we just take, when we pass from E2 to E3, we just take the kernel of this differential. And this kernel must be trivial. If it is non-trivial, then we have something in E3. So these differentials are both injective and surjective. So they are just isomorphisms. And this is the crucial observation that all this, that D2 is just isomorphism in all these situations. Well, now we can, by induction, but look, these two rows are isomorphic to each other. So by induction, we know that we have ZP here, so we have ZP here, so we have ZP here, and so on. So actually, all these cells are ZPs, but it is the result which we already know, which we already have computed this cohomology. An interesting part of this result is that now we can restore the multiplicative structure also. Let us do this. To understand the multiplicative structure, we need to apply the Leibniz rule. Okay, now I would like to draw the same picture, but instead, okay, we already understand that all groups here are ZP, so instead of writing groups, I prefer to write generators. So here we have 1, here we have iota, here we have u, and here we have iota u. What is further? Well, we know that this is D2 iota. And let us denote it. It's not convenient to write D2 iota. Let us denote it by V. So, and we know that this V is generator of this group. Here we have isomorphism, and we have this formula. But now, let us compute D2 of... first, let us start with cells with even numbers. Look, since this is generated by iota and this is by V, then here the generator is iota V, just by this multiplicative isomorphism. Now, we know that this group is generated by the image of this iota V with respect to differential D2. Okay? But we know the Leibniz rule. D2 from iota V is D2 iota multiplied by V minus, since this one has degree, iota multiplied by D2V, but of course this is 0 since D2V is 0 by dimensional reasons. So we just have V times V, so we have V squared. So we have V squared here, hence we have iota V squared here. proceeding in the same way, we can write iota v squared here, and similarly we get v cubed. So iota v squared goes to v cubed, and so on. And we see that these generated in even cells are nothing but powers of this v. Well, so we arguing inductively, we just get that these are exactly these powers. Similarly, we can consider here iota u, and what we get if we compute d2 of iota u. We get uv, yes. To be honest, we get vu, but one of them has even degree, so it's okay, they commute. So we get uv here. So generator here is iota uv, and again we have uv squared, and so on. So we see that even groups are generated by powers of v, and odd groups are generated by u times power of v. So what we see, yes, and what about u squared? What can we say about u squared? Actually, we have two possibilities. Two possibilities. Either it is v with some multiple, or it is 0. So this multiple can be 0. What can we say about u square? So we almost understand the structure of the ring. We understand the structure of the ring generated by v completely. It is just polynomial ring. But what is about u? Well, I just want to recall that the multiplication in cohomology is graded commutative. What does it mean? It means that the elements of grade 1 anti-commute to each other. So we definitely have u squared is minus q squared. What does it mean? This means that if we can study cohomology with coefficients zp, if p is odd, then this immediately implies that u squared is 0. So let us let us summarize it. Okay, so if p is odd, then u squared is 0. And look what we have here. We have that r star of zp with coefficients in zp is just, we have polynomial ring generated by v, tensor exterior algebra generated by u. This means that u squared equals 0. Well, exterior algebra certainly over zp. So this is for p odd prime. And the degree of u equals 1 and degree of v equals 2. So the second case is p equals 2. I suggest that it is an exercise, and the answer is opposite. The answer is that if p equals 2, then u squared is not 0, but it is v. So we just have polynomial ring in U. So exercise is that if p equals 2, then U squared is V. Hence, cohomology of Z2 with coefficients in Z2 is just the polynomial ring in U. Well, look, for those who studied algebraic topology, this is nothing but cohomology of Rp infinity. If we have Z2, then of course the classifying space is just Rp infinity, and since it's the quotient of infinite dimensional sphere by Z2, infinite dimensional sphere is constructible, so its quotient by Z2 is just the classifying space for Z2, and this is the cohomology of Rp infinity, and it is well known that its cohomology ring is like that. Okay, so just now I spent 10 more minutes, but let us do one more exercise. It is convenient, it is useful to make the same computation but to take R equals Z to study integral cohomology. I would like just I would like just to point out the difference with what we considered here. So we have here Z instead of ZP. And so the zeroth and the first cohomology are not ZP but Z. Okay? So what we have here we have just cohomology of ZP. Again, the action is trivial since this H is central in G. This is the same, so we have untwisted coefficients, and in both cases we have here cohomology with coefficients in Z. Again, here we have cohomology with coefficients in Z. This means that zeroth cohomology are Z in both cases. Again, here the generator is 1, here the generator is iota, and we have the same, almost the same isomorphism of bigraded ring, just we have Z here. What we see, well, but now this is the zeroth term, but the first term, what we have here? We have not Z by ZP here. Oh, sorry. Not Z, not ZP, we have 0 here. Why? Since it's home, the first cohomology of ZP with coefficients in Z is home from ZP to Z, and of course it's 0. We have no homomorphism from ZP to Z. So we have 0 here, we have 0 here, and well, and what we have here? Now we again have E3 equals E infinity, but now what should we have in E infinity? In E infinity, we now certainly have 0 here, since it is 0 already in Z2. Well, we have Z here. And what we have here? And here we must have Z, since we must, on this diagonal, we must have consecutive quotients of the group, of the first cohomology group of Z, which is Z. Okay, but at this moment, such formal speculation is not enough. The matter is that we don't know how this Z is, is related to that Z. The matter is that, okay, it is possible that this differential, it could be possible that this differential is just trivial, so that we have Z as, but if it is not trivial, but it is of finite order, then its kernel is still the group Z, so it is still okay. Well, the only thing we know is that we definitely, this is not injective. So, yes, not injective. That's true. Its kernel is some subgroup of Z. And all subgroups of Z are infinite cyclic. So we need to find out which of this group. Well, so this is a good question. How can they find out this? So there is one useful observation, that if we have cohomology with coefficients in Zp and cohomology with coefficients in Z, then there is a functorial homomorphism from cohomology with coefficients in Z to cohomology with coefficients in Z2, in Zp. This homomorphism reduction modulo P is functorial. So it goes through all these spectral sequences. So in each term, we have morphisms of spectral sequences. We have morphisms which commutes with all differentials and so on. So let us recall that we already know the result for coefficients in Zp. For coefficients in Zp, we have here Z, P, Zp. I write down Z2, E2, and we have here an isomorphism. And we have morphism from here to here. But look, here this is nothing but morphism of zero-dimensional cohomology. Zero-dimensional cohomology with untwisted coefficients is canonically isomorphic to the coefficient group. So, of course, this morphism is just reduction modulo P, just such naive reduction. We just map Z to Zp in the most standard way. So we see that the generator here, this group is unknown for us at the moment, but we know that we have such commutative diagram. If we go in this way and we go in that way, it is the same. What does it mean? We see that iota goes not to 0 here. So iota goes not to 0 in this way. So this image has, it is not 0. And we must multiply it at least by p to become 0. But a good question is it enough to multiply it by p? Maybe we need to multiply it, say, by p squared or something like that. So we definitely know that this differential is not trivial. But the question is, how can we understand? Well, I would like to say the answer. The answer is that we have Zp here, and this is an epimorphism. We know definitely that this is epimorphism. The matter is that these, why we know that this is an epimorphism? The matter is that we have 0 here. But the question is why this is exactly Zp. Why we do not have a bigger group here. Maybe it is Zp squared or something like that. We definitely know that this is a finite group and this is an epimorphism, a surjective homomorphism. So these two things we know, but the question is why this is exactly Zp. Well, there are plenty of ways to understand this. Just I don't want to stay on this for a long time. For instance, we can recall one more thing which we discussed. This is about the second homology group of G. If G is given by generators and relations, then we can write it as the group of relations, this Hopf formula. We can do it in plenty of other ways, but just I want to recall one more useful tool at this point. In our case, our group is very easy. Well, so our cyclic group of order P is just given by one relation, by one generator and one relation. Okay, so oh, sorry, I tried to do very trivial thing. This is trivial in our case. So this is 0, yes? So when we speak about homology of Zp with coefficients in Z, then we have in dimension 0 we of course have Z. In dimension 1 we have abilization of our group, it is Zp, and in dimension 2 we have 0. And now we have universal coefficients formula. Cohomology we must take we must take home from this group to ZP and ext from this group to ZP. And so we get ZP here. So this is only one possibility to understand that we actually have ZP here. There are others. Let us skip this problem. So now we know that this is ZP. This is epimorphism. So this Z which survives has index P here. Okay. And further, so we have some generator V here, which is just D2 of iota. We have ZP with generator iota V here. And again, we have this sequence of further, we again see that all these differentials must be isomorphisms. And so we have 0, 0, ZP, ZP, and so on. And again, arguing as above, we see that here generators are powers of the same V. Now it is much more restrictive. No. This is this. So the answer is that we already almost have. Well, let us just formulate this, that R star of ZP with coefficients in Z. I prefer to write down slightly. It is almost the polynomial ring with degree V equals 2. But okay, this equality means except for gradient 0. In gradient 0 we have Z here and ZP here, but in all positive gradients it is true. Okay, so this is a rather easy examples, much easier than pure braid groups from which we started, but I think that it is rather useful to discuss it in details, and we have done it. Now I suggest we do a break now, and we resume maybe in 10 minutes till 6. The matter is that I would like, after a break, I would like to start completely different topic, and it is not good to make break in the middle of it. So after the break, I would like to turn to more geometric and maybe more topological issues and less algebraic ones. So I would like to discuss some questions on Coxeter groups and how to construct their classifying spaces, and there are much more geometry and topology than algebra there. So let us stop with this algebraic part and now make a break. I suggest we resume in 10 minutes in 5:50. 5:50. Well, let's continue. I would like to start with the following observation that, well, if we have generally a group, then we have already several tools to study its cohomology. Well, either we can try to construct directly its resolutions for this group. Sometimes it is possible. Sometimes if this group is included in some short exact sequence, then we can apply Hochschild-Serre spectral sequence. But generally, if we just have some arbitrary group, we have no good tool to understand its cohomology. Nevertheless, there are several groups which are not so easy from group theoretical point of view, for which we immediately know their cohomology or homology. Let us consider just one easy example. Consider the fundamental group of surface of genus G surface. Well, we know that it is group with two G generators with one relation. That the product of commutators is 1. Okay, of course, it is not so hard from algebraic point of view, but not so easy also. But in this particular case, we immediately know all homology and cohomology. Why? Because we immediately know the classifying space. What is the classifying space for this? A classifying space for a finite group, or not for a finite, for a discrete group, for a group without topology, the classifying space for a discrete group is the same as k pi 1, and it is uniquely characterized up to homotopy equivalence by the property that its fundamental group is pi, and all higher homotopy groups are trivial, and this property immediately gives us this characterization. And in the case of this particular group pi, this is for general group pi, but now if we take this particular group pi, then we immediately see that the classifying space is nothing but the surface itself. Why? Because, of course, the fundamental group is as desired, but high homotopy groups are trivial. But the only restriction is that G must be at least 1. Yes? If G equals 0, then of course group is trivial and it is not interesting at all. But the sphere is not a spherical. The sphere has non-trivial homotopy groups. Two-dimensional sphere has non-trivial homotopy groups. All homotopy groups are non-trivial. But for starting from genus 1, we know that if we take the universal cover, then it is homeomorphic to R2. I would like to recall very briefly how we can obtain this. If G equals 1, then it is just torus and it is obvious. The universal cover is just R2. If G, so in interesting cases G greater than or equal to 2, And in this case, it is better to write down here not R2, but Lobachevsky plane. But up to homeomorphism, this is the same. Why Lobachevsky plane? The matter is that we can always endow this surface by hyperbolic metric, by a Riemannian metric of constant curvature -1. And then its universal cover automatically becomes the Lobachevsky plane. There are two results hidden in what I said. First result is that we always can equip this. There is a hyperbolic metric on this surface. And the second result is that any complete simply connected two-dimensional manifold of constant curvature -1 is isometric to Lobachevsky plane. Concerning the second result, I don't want to say why this is true, but still it is not so hard to explain why we have a hyperbolic metric here, and so there is one hyperbolic metric which can be constructed in very easy way. So I just briefly recall how to do this. Consider the Lobachevsky plane, say standard model, Poincaré model in the unit disk, and you know that we can always glue genus G surface out of 4G gon. And let us realize this 4G gon as a regular 4G gon in the Lobachevsky plane. So there exist regular 4G gons in Lobachevsky plane, and 1, 2, 3, 4, 5, 6, 7, 8. Okay. And now, okay, I would like to cut this 4G gon from the Lobachevsky plane and to glue the surface. So I would like to glue it in the standard way, this with this, that with that, and so on. These three with these three, and say this one with this. Okay? This is standard way of gluing. But if I do like that, if I cut, since this 4G gon is regular, I know that all these sides have equal lengths, and all these angles have equal value. So let be alpha. When I glue sides to each other, I glue them along an isometry. So they have equal length, so I can glue them along isometry of them. So when I do this, I have no singularities of matrix except for the vertex. All these points are identified with each other under this glue, and all these angles are joined together. So I want that I have no singularity in this point also. How to achieve this? I can vary the size of this regular 4 gon. If it is very small, then its lengths are close to then its angles are close to angles of Euclidean 4G gon, regular 4G gon. So at least they're greater than pi over 2. They're rather big. When the size of this 4G gon becomes large, then we terminate at ideal regular 4G gon, and its angles are 0. So, of course, these angles are continuous with respect to the size. So we have size, exactly one size, for which this alpha is exactly pi over 2g. choosing size, we can achieve this. When we achieve this, then this is our desired forjigon. We can cut it, glue, and we have no singularities of the matrix at all. We have no singularities inside, we have no singularities on sides, but we have also no singularity at vertex, since the sum of angles is exactly 2 pi. And that's hyperbolic metric here. And at least for this hyperbolic matrix, it is obvious that the universal cover is isometric to the Lobachevsky plane. The matter is that now let us start reflecting this for Gigon in its sides. It is impossible to draw it. You can try to find some pictures in the internet, but it is extremely hard to draw it by hand. The matter is that the process branches very quickly. But finally, we get the tiling of the Lobachevsky plane by such regular forjigons, and this tiling provides us with this universal covering. Okay, so look, this is just model example, but in this model example, we can obtain some homotopy information starting from geometry. Actually, starting from curvature. We know that the crucial point is that curvature, actually, it is not so important that it is constant, it is more important that it is negative. We know that we have negative curvature, and hence we obtain contractibility of the cover in space, and this implies that we know that higher homotopy groups are trivial, and so we arrive to the classifying space. This is general strategy. Actually, there is general meta theorem that negative or actually even non-positive curvature implies asphericity, implies triviality of high homotopy groups. And there are plenty of situations when we can when we can obtain classifying spaces using this strategy. So what is the strategy? It is not so hard to construct some manifolds or complexes with actions of certain groups. Sometimes it is possible. We just can introduce some, we can invent some explicit constructions for some particular classes of groups, of course, not for general ones. But for some particular classes of groups, assume that we have some construction of a space with its free action. But then the question is how to prove that this space is contractible. If we manage to prove that this space is contractible, then its quotient is automatically k pi 1, and we can obtain some knowledge about group, about its not only homology. Actually, knowing explicitly classifying space is useful even in its own, not only because of homology. Classifying space is a very important thing in understanding a group. But now let us discuss what does it mean non-positive curvature. First of all, in differential geometry, there is notion of, okay, for two-dimensional manifolds, it is just non-positive Gaussian curvature. It is enough. But what we need to have for higher dimensional manifold, if we have a Riemannian manifold, then there is a notion of sectional curvature. There are several possible definitions. I recall those which requires the smallest amount of things. You can write down a Riemannian curvature tensor and so on, but I don't want just to say those definitions which doesn't require any knowledge, any general knowledge in differential geometry. Look, assume that you have some Riemannian manifold and you take a point on it and you consider two geodesic rays from this point. For simplicity, let them be orthogonal to each other. Let us consider two geodesic rays, and we take on both of them you consider segments of length epsilon. The question is, what is the distance between those 2 points? Well, let us make two easy computations. First of all, assume that we are in the Euclidean plane. Then I think you can immediately say me the answer. The answer is square root of 2 times epsilon. Well, I prefer to work not with length. Length is not so good. It is better to consider square root of length. Well, then the square root of length is just 2 epsilon squared. Okay, let us keep this in mind, but let us consider another, but also rather easy situation, somewhat, but still somewhat more complicated. Let us consider a sphere of radius r, round sphere of radius r, and ask the same question. So I've got sphere of radius r. I have a point. Starting from this point, I consider two geodesics. What does it mean? This means that this is a great circle. Geodesic is just okay. And I go by, okay, I have arcs of length. Yes, length on a sphere is, of course, length in not in the ambient 3 space, but length along the sphere. So I consider Riemannian metric on the sphere. I go by arc of length epsilon. And the question is, what is the distance here? Let us make this computation in this particular case. First of all, what does it mean that we have arc of length epsilon? This means that the central angle is epsilon over r. Yes? So we have such. The angle, this is the center of the sphere, and these are 2 points, A and B. Okay? The angle is epsilon over r, so we can easily write this in coordinates. So I prefer to, the first coordinate axis will be through A, the second will be in the, so that this geodesic is in the plane OXY, and the second geodesic is in the plane OXZ. Well, then A is just 1, 0, 0. B is okay. We have this angle epsilon over r. So this is of this is not 1. This is r. Our sphere is of radius r. So here we have r cosine of epsilon over r, r sine of epsilon over r, and 0. And C, the third point, is of course the same, but 0 here and r of sine epsilon over r here. Well, so what can we say? I am interested in the distance between B and C. Hence, I am interested in this distance is if the length, if the angle here, the central angle is phi, then this distance is just phi times r. So I need to compute this angle phi. So let us start with its cosine. What I can say about its cosine, I can extract it from the scalar product of these two guys. Well, and I immediately see that cosine of phi is the scalar product of these two divided by r squared. So this is just the square of cosine of epsilon over 2r. Okay, of course, when epsilon is small, then phi is also small. And of course, the first term will be just similar, yes? The matter is that when epsilon is small, we are very close to Euclidean situation. I would like to study the next term. So the next term, the first term is epsilon squared. The next term is epsilon. Of course, cosine has only even powers of epsilon. So I would like to consider these equality till epsilon fourth. Epsilon sixth is not interesting to me. Okay, let us do this. So epsilon or phi, they are of the same order. So I would like to this cosine is like that, yes? Plus 6. Okay? And the right-hand side, I have the same for epsilon, but for epsilon over r. Okay? Plus epsilon fourth over 24 r fourth. This plus 6, and this is squared. Okay? When I open brackets, I can neglect everything which contains epsilon of power 6 or higher. Let us draw just, okay, y1 minus like that, yes. Oh, what I'm doing, sorry. Well? Yes, yes, that's true, of course. And yes, but what I want to do, Okay. uh, well, let's proceed. What is the coefficient of epsilon 4, fourth power here? We can first take the square here, and we get 1 over. So I am interested in this coefficient. Yes? We have 1 over 4 from here, and we have 1 over 12 from here, and so it is 1 over 3. Yes? Well, no, I have already this one I have already multiplied it by 2, but the square of this one I don't want to multiply by 2, so this is exactly 1/3. Okay, but what I am interested in? I am interested in expressing phi from epsilon. Well, how can I do this? So, okay, I have two small parameters. Actually, let us simplify our task. I have two small parameters, but look, I have only even powers everywhere, so it is easier to obtain. It's easier. Let alpha be epsilon square. Even let it be epsilon square over r square. I prefer to simplify my task. Well, and beta is phi square. I just want to have two small parameters. And I have such relation that 1 minus. Okay, of course I can cancel these ones. It is not so interesting. So I have minus beta over 2 plus beta square over 24 plus O big of beta cube equals minus alpha plus alpha square over 3 plus O big of alpha cube. Well, I would like to express beta from alpha. Well, how to do this? No, we have no 2 here. We have 2 here, but once it's squared, we have no 2 here. Exactly this. Well, how one do this? This is just the rule how to express alpha from beta. Okay? Oh no, I prefer to express beta from alpha. Okay, I just would like to write it as a series. What is the first, the first term, the starting term? The starting term we see easily from here. The starting term is minus 2 alpha, not minus, it's just 2 alpha. It is not surprising, it is just this one, yes? But now the next correction term is some constant c, I don't know it at the moment, alpha times alpha squared, plus O big of alpha cube, it is not interesting to me. Now to find this constant c, I must substitute this beta to here. And I get the constant c from there. I must substitute and consider the coefficient of, if I, actually in the same way, we can compute all coefficients if we need. but we need only the first one. Let us substitute it here. What we get, I write down the left-hand side up to O big of alpha cube. It is not interesting. So what we see here, minus beta over 2 is minus alpha minus c over 2 alpha squared. Well, and now beta squared over 24. I need to square this and divide by 24, and I'm interested only of alpha squared. So only this is interesting to me, 4 alpha squared divided by 24, so alpha squared over 6. Okay? Plus O big of alpha cube. And we see that we must get this is equal to that. Well, so we see that minus c over 2 plus 1 over 6 is 1 over 3. And from this we see that c equals minus 1 over 3. Yes, that's right. Okay, this is exactly what we want. So now let us return to our initial notation. So we see that this is about beta. We see that phi squared is 2 alpha, so 2 epsilon square over r square minus 1/3 of alpha squared of epsilon fourth divided by r fourth. Well, plus O big of epsilon 6, which is not interesting to me. But I'm interested not in phi square. Phi is the central angle. So what is interesting to me is L squared, the distance squared, which is phi squared multiplied by r squared. So, well, from here we immediately obtain that L square, which is r square multiplied by phi square, is 2 epsilon square. And we are interested in this first correction term. First correction term is 1 over 3 r square epsilon 4. Okay. So this is exactly what, this is exactly what we are interested in. Look, if we are on the Euclidean plane, then the distance is just 2 epsilon, the square of distance is just 2 epsilon square. If we are on the sphere of radius r, then there is correction term. The main term is still 2 epsilon square, but this next term is like that. For instance, if we are on the sphere of, but look, this 1 over r square, it is exactly the Gaussian curvature on the sphere, of the sphere. We also know a good example of metric of negative constant Gaussian curvature. This is Lobachevsky metric. In the standard Lobachevsky metric is of curvature -1, but of course we can normalize it so as to get any negative Gaussian curvature. Exercise that on Lobachevsky plane, if you make the same computation on Lobachevsky plane, the result is result is plus 1 over 3. So generally, on two-dimensional manifold, the coefficient here is minus 1 over 3 times Gaussian curvature. And so it is a natural definition of sectional curvature. Sectional curvature, okay, we started from a point on a Riemannian manifold, and two